welcome everybody. We are glad to introduce our next two speakers. Hitesh Dhawan is currently pursuing a Bachelor's of Technical Aerospace Engineering from the University of Petroleum and Energy Studies in Dehradun. He's worked on the design of supersonic business jet engines and is capable of achieving Mach 1.15 over land and Mach 2 over sea. For AIAA gas turbine engine design competition in 2020, and also on the proposal for inflatable habitat design for Indian space exploration missions to ISRO. He's interested in the field of propulsion and has done a minor on the development of reaction control systems for a 6U CubeSat, which helps in changing its attitude to perform various maneuvers. He's also has experience working on hybrid rockets during his summer internship, in which he worked on design studies based on hybrid rocket systems. He is joined by Paras Adlakha. He's aspired to the science field for studies because he found himself curious to know how things actually work or how the universe is defined by the laws and theories given by researchers and where those laws are not applicable. His interest in aerospace developed at an early age, and he was very fond of aircraft. He opted for science and mathematics in higher education because of his habits of taking challenges. He participated in the International Mathematics Olympiad and National Science Olympiad. After that, he thought engineering was the area where he could learn the most and explore his fields of interest. He's now pursuing a Bachelor's of Technical Aerospace Engineering from the University of Petroleum and Energy Studies. And from the start of engineering until here, he's experienced a strong development in his background in the field of aeronautics as well as astronautics. They are going to be speaking to us today on the topic of next generation power for Martian life. Welcome, Paras. And yeah, welcome.
So good afternoon, everyone. I hope I'm audible to all. So let's begin. The topic for today is next generation power generation on Mars. We are going to discuss about the supercritical Brayton cycle that will be using supercritical carbon dioxide. Now let's discuss why we chose Mars and not any other planet.
Today Mars is the most captivative topic for the researchers due to following reasons. The presence of atmosphere in the on the Mars prevent the cosmic radiation, even if it is very thinner than the Earth atmosphere. The promising nature of water in Martian soil can be used during the manned mission. The Mars is the only planet after Earth which is present in the habitable orbit region in the solar system, which makes it not too cold and not too hot for living. Mars is having the gravity of around 38% that on Earth, which is found to be sufficient for humans to adapt on the Martian surface. The rhythmic cyclic of day and night is too similar as that of the Earth, due to which the Martian day is of around 24 hours and 39 minutes and 35 seconds. Also, the Martian surface receives around a considerable amount of solar radiation. So coming to our topic, next generation power for Martian life. So we start from as we all know, the power is the major factor while designing a space habitat over the Martian surface. The most optimistic source of power generation on Mars will be solar radiation. As I said earlier, that Mars receives a considerable amount of solar radiation. The direct use of solar power or simple power generation cycle like Brayton or Rankine cycle will not be efficient on Martian atmosphere. The Martian atmosphere consists of around 95.32% of carbon dioxide, from where our research begins. By making the use of this carbon dioxide, which is carbon dioxide rich atmosphere, we analyze the concept of producing the energy from supercritical CO2 hybrid power cycle, also called supercritical hybrid Brayton cycle. So here comes our methodology.
Maybe I can continue from here for methodology for here. Am I audible to all?
Yeah, you sound good, Hitesh.
Okay, so let me explain this. So methodology is what we're trying to do is we will first of all explain our objective for our research, then what all has been already done, the literature survey, the concept for our basic understanding of what how the power generation cycle and how the Brayton cycle will actually work, and then we will be giving you the data, the statistic, the data, and try to show you the analysis or comparison between the various ideal Brayton cycle and the real Brayton cycle for supercritical carbon dioxide. And then we will show you the calculations that will be required for the solar calculations and the size of the solar panel that will be required for the total power plant in order for the heat to be added. And then we will talk about the challenges and the practical applications, and finally we will conclude. So the objective, if Paras can is he audible?
The objective, the manned Mars mission will require a good amount of power generation, because a single trip of Mars requires around 30 months of time until they come back on Earth due to orbital properties of Earth and Mars. For carrying out in situ operations like drilling, production of oxygen, extraction of water, etc. on the Martian surface, a power generating system with a reach assuring potential is required there on Martian surface. Though the solar radiation over Martian surface is very high as compared to the Earth, but still atmosphere blocks it by around a considerable amount. That's why direct use of solar panels for generating the power cannot be used on Martian surface.
Our objective will be how Brayton cycle is helping us in how by using supercritical carbon dioxide our Brayton cycle is getting more efficient, and how it is like we are having a size reduction in case of because to build a huge power, to have a huge power generation plant, our size will decrease considerably, and we will see in the coming slides. So the initial research.
So coming to initial research, over the period of research, the power generation from the solar and nuclear generation on Mars shown the good result while taken into consideration during the analysis. The supercritical Brayton cycle is the good alternative of simple Brayton and Rankine cycle, where the medium of flow is CO2 instead of air, because it is more efficient as well as optimized than the any other power generation cycle. The SCO2 cycle or supercritical Brayton cycle can also be used in the coal-fired power plant to increase the efficiency of power generation. Earlier, several recompression and pre-compression cycles were analyzed during the research of our supercritical Brayton cycle. So here's the data showing the Martian atmosphere. So here is a composition. As I said earlier, the carbon dioxide is around 95.3% in the Martian atmosphere, and here is the atmospheric conditions. As we all know, the Martian atmosphere is around 100 times thinner than the Earth. The ambient pressure conditions is around 610 pascals, which is less than 1% of the Earth, and temperature at 0 kilometer of the Martian surface is around 228.5 Kelvin. So coming to supercritical Brayton cycle, so here are the inlet conditions for supercritical CO2 cycle. The pressure at the inlet is required around 7,377.3 kilopascals, and the temperature of 304.1
Kelvin. Density of CO2 is 1.98 kg per meter cubic, and specific heat at constant pressure is around 0.8312 kilojoule per kg per Kelvin, and the gamma value of CO2 is around 1.2941. So coming to our concept of next generation supercritical Brayton cycle, the supercritical Brayton cycle will be used to produce the power required for space habitat or any manned mission on Mars. The SCO2 cycle is used to increase the efficiency of the simple Brayton cycle. It is assumed that the CO2 will be pre-compressed from the pressure of around 610 pascals up to the pressure of around up to the pressure of inlet condition for the supercritical Brayton cycle, as I said earlier, is of 7,377.3 kilopascal. It is used in a hybrid mode, means it will get the heat input from the solar panels instead of fuel-based combustion chamber, which are the conventional one. The heated CO2 is passed through the turbine, which start rotating. As a result, the initial power cycle begins, and thus from the turbine, our electricity is generated, which can be used directly from the consumption in Martian habitat. In order to increase the efficiency of a turbine, we are using a regeneration Brayton cycle. So here's a ideal Brayton cycle. We have used a pressure ratio of around 10.5, and
so for ideal Brayton cycle, am I audible to all? Am I audible, please? So in the ideal Brayton cycle, what we are Am I audible?
Yes, you're audible.
Yes. Yeah.
We can hear you.
Then, okay. Then, so I was speaking about ideal Brayton cycle. So, in the ideal Brayton cycle, what we're trying to do is we are initially taking the supercritical conditions at the inlet of the compressor. In an ideal Brayton cycle, what happens is we have three processes. First is compression, second is heat addition, and then is expansion. For compression at the inlet, we have the pressure conditions of 7.3 megapascals that you can see for the supercritical CO2. That means we are taking the at the inlet, the fluid is already at supercritical conditions. So we can well imagine that when the fluid is at supercritical conditions, the turbo machinery design itself becomes a challenge because of the stress analysis and the thermal stress forces that it has to face, because it has to now undergo now compress a highly dense fluid. So so we will be using 4 compressor stages in this case, provided the pressure ratio per stage is around 1.8. And the total pressure ratio for us that will be required for ideal Brayton cycle will be around 10.5. In this case, because it's an ideal case, we are not assuming any losses, pressure in any form, whether it is pressure or any other form. We are also not including any viscous forces. The specific heat constant and the mass flow rate here is assumed to be around 100 kg per second. Now, as you can see in the table and the data provided, what was happening is initially when we are increasing the pressure, we are trying to take it to the to around 6.41, that is into the combustor. Here in our case, the combustor will not burn any fuel because we are using solar radiation as a heat source. What will happen is in the combustor there is a heat exchanger. As a result, the energy that is generated from the solar panels is being used in order to heat the supercritical carbon dioxide to a higher temperature. From there, it will be moved to the turbine, where it will help in providing the necessary where the necessary expansion will take place. As a result, the energy is produced, which will help in further rotating the dynamo, and we will have the energy produced by the ideal Brayton cycle. Now, the advantages that we are gaining from here is, number one, that is this. First of all, let's try to compare it with the real Brayton cycle. So in real Brayton cycle, what happens is the initial conditions remain the same. That is for the supercritical state, carbon dioxide entering entering the compressor. And we also want to tell you that the turbine is not, it's not an open Brayton cycle. We have a closed Brayton cycle over here. So the circuit will always be closed. So initially we need to take it to the supercritical state in the ideal case, but in the later on cases, it is not the same. We will be continuing the same fluid inside the whole cycle. In the real cycle, we are including the losses. And as you can see in the graph, as a result, it is no longer an isentropic case. Because in ideal, we are assuming the isentropic case, the lines are straight, but here the lines are curved due to the losses that we have to include. Now, in regenerative case, what we are trying to do is we are trying to add heat in separate stages. So we will be using 2 combustion chambers. So what happens is, first, initially, we try to raise the temperature to a certain limit. In this case, we are trying to enter the supercritical fluid again, and we are trying to raise the temperature to 926.85 degrees Celsius. And then when it gets exit out due to expansion, the temperature decreases. Again, we try to raise it up. This helps us in increasing the overall efficiency of the system. As a result, the overall efficiency, which has already increased due to by using the supercritical fluid, and with configuring it with the real regeneration cycle, we get better results that can be seen in our graphs. From here, as we can see, from ideal Brayton cycle on comparison from the ideal Brayton cycle to the ideal regenerative cycle, we can see a significant increase in the efficiency. Then what we are trying to do is, by inculcating the losses also, like all the losses that we can have is in case of compressor, because of like the flow separation and because of the viscous forces, the overall regenerative cycle will have somewhere a little less efficiency as compared to the ideal case. But still, the real case is way better, because by using the regeneration cycle, we are trying to keep the temperature in the fluid kind of constant, nearly unilateral or linear. We are trying to heat it, add the heat. Now, as we can see in the graphs, for the PV and TS curves, in our case, what we are trying to do is.
Tash, we have about 5 minutes.
Okay. So we are trying to compare these cycles with the initial cases. And then what we are trying to do is we are trying to calculate our solar value. So solar calculations are done by calculating the power rating, and we are using the sun power Maxian 3, which having the efficiency of 22.6%. As a result, we came to know that in order to generate the average space habitat consumption of around 170 kilowatts, we will be requiring an area of around 1276 meter squares of solar panels. Now the challenges, as I have explained earlier in the beginning, are about the turbo machinery design because of the stress analysis, thermal analysis, and the flow separation. And again, we have to achieve the supercritical state, which itself is a challenging task initially, though it is easier as compared to the steam cycle or runtime cycle. In conclusion, we can tell that because we are using solar instead of any other fuel like thermal, we are not burning any fossil fuels, or we are not using any other thing. Even though on Mars, we are using the same carbon dioxide that is available outside. So it is finally highly eco-friendly for us, because provided the space habitat, we are not consuming all the resources on that planet. We are using the resources of that planet only. We don't have to carry it from Earth. And then the size of the power plant has reduced significantly as compared to all other cycles. So yeah, I would like to conclude. Thank you.
Thank you, gentlemen. Very nicely done. We have a couple of questions so far, and if we have any other questions from the audience, please type those into the chat window, and I'll ask them to Hitesh and Paras. Let's see, the first question is from ET. He says, how are you going to collect the required amount of carbon dioxide from the atmosphere?
Okay, so that's a nice question. Actually, what we're trying to do is initially, when we're initially we have to carry all the air in the same time. We will be collecting it, and with the help of we have to carry it a section or carry some source of battery from the earth. That will help us in acquiring all the air, and in order then we will be kind of with the help of, because we are using a closed Brayton cycle here. So initially we will be getting the carbon dioxide, which is 95.36% of the atmosphere. We will be trying to separate it out, and we will be taking it to the supercritical state. We will have to just spend energy once for this case. Because of the closed Brayton cycle, we will each time we will be trying to rejuvenate it. Rejuvenation will take some energy, but the energy taken will be significantly less as compared to each time we are not going to collect it each time. That's why we are going to collect it only once. I hope I answered your question.
Thank you. Joel asks, what is the fuel that's being combusted?
So Paras is answering.
As I said earlier, we are using the supercritical Brayton cycle in a hybrid mode. So we will be using a solar panel for the instead of a conventional solar panel heat from instead of the conventional combustion chamber. We will be using the heat directly from the solar panel.
So what we are trying to do is we are trying to provide the solar. We are trying to use the solar panel, and then we're using the heat exchanger. In order, the heater will be already have some heat. We are trying to raise the temperature of supercritical CO2 that has entered into the combustion zone. It is not actually the combustion is named here because of the Brayton cycle conventions that we are using. It is actually a heat exchanger that is generally raising the temperature of the supercritical CO2 that has entered the that particular heat exchanger zone.
ET asks, could this same technology be used for CO2 capture on Earth?
Can you please repeat?
Could this same technology be used for CO2 capture on Earth?
Yeah, but there's a difference. On Mars, it is around 95.36%. On Earth, it is hardly around 1%. So using the same technology, the efficiency will not be the same. Here on Earth, we will be spending a lot of energy in order to get that CO2. Though we can do that, but it will be not that efficient. The efficiency will decrease significantly for our case. But we can still, it will be expensive, but it will help us, because if we are using a closed Brayton cycle, it will be a one-time expense. But in overall case, if we use an open Brayton cycle, it would not be efficient that much for an open Brayton cycle.
Thank you. Frank asks, can you estimate the cost of the Brayton cycle system to generate electricity compared to solar PV system of similar capacity? So how does it compare to solar power generation in terms of cost?
I'm sorry, I'm not. Can you please repeat?
How does the Brayton cycle system compare to a solar power system in terms of cost to generate electricity?
Okay, in terms of cost. So what about in a normal Brayton cycle, we are burning fuel. So when we are burning fuel on Mars, now we are coming on Earth when we are trying to compare the cost. Because on Mars we have to, we are not going to carry the fuel from Earth, and we are not going to combust it. But on Mars we are using it from there, so it won't be that it won't be expensive. It will be one-time expense, as I said earlier. But on Earth, if we are trying to compare it, what happens is when we are trying to burn the fuel, the cost of fuel will be added to here. But when we are trying to use it on Mars, there will be no cost, because we are just capturing it from the carbon dioxide from the atmosphere, and we are trying to separate out the carbon dioxide, taking it to the supercritical state and using it in a closed cycle, in a closed loop. We are not burning any fuel, so the cost will be significantly reduced in our case, because we are not going to use the fuel.
Thank you. Let's see, I don't see any more questions here from our audience. Does anybody else have any questions? All right, well, if you guys want to stick around, Hitesh and Paras, thank you for your presentation. If you want to stick around for a few minutes, if anybody else thinks of any questions, I'll share those with you. And we have about 3 minutes before our next round of discussions begin. So that'll give everybody some time to make their way over to the next rooms. Thank you. Let's see.
Can I ask a question orally?
Sure, go ahead, Frank.
Okay, I want to get back to the cost of the system to generate electricity. What I was interested in knowing was the cost of the entire system, which includes your solar arrays to generate heat, plus the cost of the Brayton cycle equipment, and in comparison to something that's strictly a solar photovoltaic system. Do you have an estimate of those costs?
Actually, we don't have that estimate, but what we can tell theoretically by understanding your question is that when we are trying to build an ideal Brayton cycle or the Brayton cycle based on supercritical states, we have to design the turbomachinery components. And designing turbomachinery components will definitely cost us more, and it will be expensive as compared to the normal photovoltaic cell. But the advantage is that when we're using a photovoltaic cell directly, the efficiency is very less. It is, as you can see, it is around 22.6%.
Yeah.
So even if you are using a rating of 400 watts, suppose you are using for a 1 meter square radius, for a 1 meter square area, and you have the power rating of 400 volts, you will be just getting around 22.6% of that 400 volts only. But if you use an ideal Brayton cycle or you use supercritical Brayton cycle, for in our case, with regeneration that we are using, you will have around 50% or 55% efficiency in real case, okay? Provided we assume all the losses, and we have further, if you are using heat exchangers, there may be some losses further, but by design, though it is, you have to design the turbomachinery, designing turbomachinery will cost us initially, but we have to spend the money on manufacturing one time, but the efficiency will kind of in the future return that cost, because we don't have to spend that. We will be gaining in terms of efficiency in this case. I hope I have answered your question.
Yeah, I guess you've got to demonstrate it. Yeah.
Yeah, I think, yeah, hi, I'm Ramesh here. Thank you, everyone. So I think Hitesh has very clearly mentioned the question which I asked by one of the panelists or might be the audience. The cost itself is justified by the efficiency itself, because when I'm looking for the solar plate and the photovoltaic and all the crystalline material, so far the latest research says that you cannot go beyond of the 30%. So practically it's not possible to go beyond of the 30%. So definitely when you're looking for the supercritical, so this gap of 20 to 25% itself is justified a lot. So I think this is the next generation, I can say, the power needed either is for the space or maybe for the land-based power plant. So this is the new era of, you can say, the power generation.
I guess I'll answer that just by saying that the most efficient system in terms of cost per unit mass is a nuclear power system, and yet the solar system turns out today to be cheaper because of the total cost of building it and maintaining it. And that's my question regarding the Brayton cycle. You know, the cost of that equipment to compress the gas and get the power out of it is all part of the total system cost. And I would just like to see some estimate of what that is.
Yeah, so I'm agree with you. In fact, the now you told that of course the nuclear one is the very cheapest one overall cost, definitely. But the investment or initial cost is going to be very high. But in totality, over the year and a year, your what we can say the return is going to be very high, and that's why the people are looking for the nuclear. Only safety hazards and all these things you have to take in care of that. So as of now, I think the cost estimation is not included in the presentation, but definitely I think these are maybe included in the future whenever there's some other presentation or other forum is there, definitely is going to present there.
Yeah, I'm
And
encouraging you to do that
Yeah,
because I tuned into this especially because this sounds like a great idea to evaluate more fully.
so only challenge in this
Uh,
supercritical is to design a complete turbo machinery, because when you're looking for the turbo machinery part, so when it reaches to the supercritical region, so the behavior of the turbo machinery is going to be changed very drastically. So that's the only challenge normally we are facing right now. Yeah, Hitesh, over to you.
I would like to add on that. Well, I have mentioned in the challenges, as you can see, the turbo machinery. The turbo machinery challenges are like whenever we are trying to design a turbo machinery for it, for the compressor, we generally try to use a turbo alternator compressor because here we have to compress an already compressed gas that is already at 7.73 megapascal, that you can understand, okay? But we are gaining advantages each time we have pros and cons for the same thing. So the gains are more in the terms of efficiency that the system will achieve in the later on stage once it has started running. Initially, we have to spend some energy in order to raise to the supercritical state, as compared to what you mentioned is nuclear options. When you are setting a nuclear system over there, you will have to spend at least a lot of power, because you have to take a lot of precautions for that also. In this case, you don't have to be because in comparison, when you are doing, you have to take into account all the factors that you are getting. And in our case, we are getting a significant size reduction. So it will be comparatively compact as compared to a nuclear power plant or any other thing that you will be using. Further, if you are solely dependent on solar power plant, like you mentioned about the photovoltaic cell, it won't help in that way. It won't help us particularly because the efficiency is very small. You will have to set up a very huge solar array over there in order to gain or in order to fulfill the requirements of the space habitat that they will be using. Further, you have to maintain it regularly, though in our case also, but we are using it as a heat exchanger, and we are using the solar radiations completely to the maximum extent that is possible for our case. That's why we have used what is available in the recent grounds. Okay, I've got a question.
Okay, well, thank you very much.
Understand. I just got a question.
Thank you for taking the time to answer those questions, gentlemen.
Okay, thank you.
Does anybody else have any questions? Let's see. ET says, how do you capture the CO2 in the first place? I understand how to collect rainwater, but not air. What system will you use to do this?
If I have to demonstrate in a very easy words, I would say like you can use kind of what we're trying to say is you can kind of have you seen the vacuum kind of thing in your vacuum cleaner type? We are trying to suck the air. We're trying to keep it, we're trying to distillize it, and we're trying to separate it in carbon dioxide and its separate components. We're then trying to raise it to the supercritical state. In very easy terms, is we are trying to take in the whole atmosphere, the whole around the air surrounding it. Then we are going to trying to convert it for the supercritical state. I hope I answered your question.
Yeah, thank you for breaking that down. That was good. That was a good explanation. Any other questions? I don't see anything else. That was excellent. Thank you very much, Hitesh and Paras. That was a great presentation.
Thank you, everybody.
We'll leave this open for a few more minutes. If anybody else has any other questions, we'll close here in about 4 minutes.
Yeah, sure.
Thank you. And is Ramesh your professor?
Yeah, he's a mentor.
Okay, excellent. You guys did a great job of answering those questions.
Thank you, sir.
Thank you very much for your preparation and your presentation. That was great.
Thank you, everyone.
We'll see you
Thank
later.
you, everybody.
Thank you, everyone.